Hello, and welcome to the SAMPE Q&A session for Advanced Design and Analysis. Thank you all for joining. I'd like to make you all aware that this session will be recorded and posted on the SAMPE website for on-demand viewing. If you have questions throughout the duration of the session, please type them into the QA feature found on the control panel of your Zoom meeting window. My name is Louis Dorworth. I am the Direct Services Manager at Abris Training in Reno, Nevada. My background is in tool design, tooling, manufacturing engineering. Spent some time in M&P and R&D before I took to teaching this subject matter. So briefly, that's who I am, what I do. What I'd like to do is go immediately into the panelists that we have today. We have 5 different panelists with different papers, and we will be asking questions of them today. The first panelist is Dominik Dörr from SIMUTENCE. Dominik has studied mechanical engineering at the Karlsruhe Institute of Technology, KIT, in Germany, with a specialization in lightweight design and theory of mechanics. Between October 2014 and October 2019, he worked on thermoforming simulation of thermoplastic tape laminates with his doctoral studies at KIT and at the Institute of Vehicle System Technology at the Department of Lightweight Technology. In February 2019, he founded, together with 2 colleagues from his doctoral studies, SIMUTENCE, I hope I'm saying that right, you can correct me if you need to, which is a spin-off company from KIT focusing on virtual process chains for fiber reinforced composites and hybrids. His paper was titled "On the Relevance of Thermomechanics and Crystallization Kinetics for Finite Element Thermoforming Simulation." So thank you, Dominik, and we'll get right back to you here with some Q&A in a minute. Okay, next up, Pierre-Yves Lavertu, MSC Software, e-Xstream, or e-Xstream, yeah, okay.
You got it.
Have we got, okay. Pierre-Yves has a bachelor degree in material engineering from École Polytechnique in Montreal. Was an interior FAA stress certification and knowledge consultant for Dassault Systems out of the university. After 5 years with Dassault, Pierre-Yves moved to a finite element and analyst position at Convergent Manufacturing before landing at e-Xstream as an application engineer. His paper is titled "Holistic Design Analysis Approach for Additive Tape Placement Process." So we'll get back to you with some Q&A here in a minute. Third speaker, Hugh Mcilroy from Dow Chemical Company. Hugh is an expert in numerical techniques, material characterization, and engineering design. She has led several design projects for the packaging and specialty plastics, polyurethane industrial construction, performance silicones, and Olympic and sports solutions business units at Dow. Boy, that's a handful. Moreover, she's an expert in digital image correlation techniques. Hugh obtained her PhD in mechanical engineering from Texas A&M University in May of 2016. While completing her PhD, she had worked at NASA Langley Research Center as a space technology research fellow prior to joining Dow. Her paper is titled "Modeling the Temperature-Dependent Structural Performance of Rigid Polyurethane and Polyisocyanurate Foams Using Mean Field Homogenation and Finite Element Analysis." So, speaker number 3. We'll go on to speaker number 4, Scott Nesbitt. Scott is with the University of British Columbia Composites Research Network. Scott's background, he has a master's, is a master's student at the Composites Research Network, studying the experimental characterization of impact damage at various or varying strain rates. Scott received his Bachelor of Science degree in mechanical engineering from the University of Calgary, where he was extensively involved with the solar car team. Great projects. Through this student team, he worked extensively with composite materials as the team developed their first car with all composite chassis. After graduation, Scott worked as a product development engineer with Luxfer gas cylinders, handling the design, testing, and certification of composite overwrapped pressure vessels. His papers titled Transverse Impact Simulation of CFRP Panels Using Continuum Damage Mechanics Model in LSDyna, LSDyna?
LSDyna, yeah.
Okay, all right. So thank you, Scott. We'll get back to you here in a minute with some Q&A. Last speaker, Daniel Rapking, University of Dayton Research Institute. Mr. Rapking is a research engineer in the Structural Materials Division of the University of Dayton Research Institute. His work is focused on computational modeling of composite materials utilizing discrete damage methodologies. In addition to computational modeling expertise, Mr. Rapking has extensive familiarity with experimental test methods and non-destructive inspections via X-ray computed tomography, so CT scan. On the development of a, his title is on the development of a computational design methodology for tailored fiber placement preforms. Looking forward to the Q&A on all of these. Okay, so with that, go to my notes here. We have some questions for each, and I'd like to go back and start at the beginning with Dominik, and we can ask some questions, and if the audience has any that they put into the Q&A, we can pick up from there. I've got a couple of questions for you out of the chute. Can SIMUTENCE-based simulation help optimize the thermoforming process parameters?
Yeah, so absolutely we can do that. So the main driver for finding processing parameters or processing parameters influencing the thermoforming behavior for thermoplastic UD tapes is that on the one side that we have the geometry you want to form, and on the other side the laminate layout. So this is basically what all of the approaches can account for, which are out on the market. But a special thing, what we do is to account also for the temperature and the crystallization kinetics of semicrystalline thermoplastics. And this is something which is usually not considered in thermoforming simulation. And what our study has shown is that this has a seminal influence on the thermoforming behavior. And then coming back to your question, if we can consider the processing parameters, we know for thermoforming processes that the initial laminate temperature and the tool temperature are influencing the thermoforming behavior. And this makes our approach kind of very applicable to predicting also these processing parameters because we account for them. And this is something what is not always done in existing approaches for thermoforming simulation.
We all know how important it is to be able to get that crystallinity in thermoplastic materials. Another question, do the UD and fabric model assume inherently good wettability between the fiber and matrix, or are there other assumptions?
Yes, so we assume this. So what we have is a mesoscopic approach. So this means that we model the single plies of our stacked laminate, but we do not account for separately for the matrix and the fibers. And this means that we have to assume how the wettability or how the situation in the pre-break looks like. And this does not change throughout the simulation. So this means there is no matrix fiber flow or any impregnation modeled in our approach, because this happens on another scale we can't account for in our mesoscopic approach.
Okay, very good. Thank you. Thank you, Dominik. I'm sure we'll come back with another question. If anybody has a question for Dominik, please feel free to put that into the Q&A box, and we'll come back around. Next, we're going to talk to Pierre-Yves Lavertu. And Pierre, I do have a question for you, and perhaps we'll get some others. Do we really have all the input properties of the constituents for such multi-scale modeling?
Generally, when someone or we expect someone to go into this work, we would first have to go through a calibration process for the material model generation. And for this, there is going to be some standard testing needed at a sample level. So any type of unidirectional samples. For the study that we've done, we've worked with generic materials for which we had the data, but assuming that everyone built parts out of different material coming from different material suppliers, there might be some calibration needed to be done for that specific material.
Okay, thank you. Next, I have a question for Hugh Mcilroy from Dow Chemical. Hi, Hugh. The tools you use, Digimat, looks helpful in designing new composite materials. Can it design materials with different microstructures, and can you elaborate?
Yes. So actually, Digimat is a software package, and it has multiple modules that can do many different things. And the main module that I use in my work is called the MF module, which is the mean field homogenization module. And I use it to simulate forms, but it can be used for composite. And actually, this tool was first developed to model composites. And so we can use it to model multiple types. So matrix with multiple type of fillers. So it could be job fibers, continuous fibers. You can use it to model fabric, multi-layer composites. And then the fillers can be multiple shapes. So you can use it to model spherical inclusion, elliptical shape, also multiple phase of inclusion. So you can have more than one type of fibers or fillers that you use. And then the filler can be, multiple phase. So it could be like, for example, a sphere with a core and a shell. So it's very powerful. Yeah.
Okay, so down to the microstructures. Okay, well, thank you. And next, I have a question for Scott.
Go ahead.
Scott Nesbitt. Why do you choose LSDyna for this work?
For this work, there's a few reasons, and I'll start off by saying that any finite element simulation software, particularly the explicit solvers, would work as long as you have an interlaminar damage model that works with composite materials, and then also some way of accounting for interlaminar damage model, and then some way of accounting for interlaminar damage, typically the cohesive zone model. We chose LSDyna specifically because our project was more focused around materials for the automotive industry, and many of the automotive OEMs use LSDyna for their crash modeling of vehicles. So it seemed to be a good fit there in terms of, if anything came out of this that they want to use, it's already kind of in the most common software. We also have a pretty extensive history with LSDyna. We've been working with it in our group, the Composites Research Network, since the 1990s. So we've already got some of the code, or all of the code implemented into it, and it's the CODAM2 material model is actually built into LSDyna as a predefined material, MAT 219. But we have recently actually started implementing it in Abacus as well. We've done a few preliminary tests with that. I suppose the other big reason was just that LSDyna does have a very well respected contact models, contact solvers, and that's quite important for this type of impact simulation.
Absolutely. Okay, thank you. Daniel, we have a question for you. What is the selection rationale in terms of properties for the stitched fibers such as Kevlar or carbon, Nicolon, etc.?
So for the work that we were doing in this project, we chose Kevlar as the stitching fiber, given its unique ability to wet out well with the resin system that we're utilizing, and its well-documented use in providing reinforcement in various forms of textile composites and other things in literature that have been done to show that providing that Kevlar stitching does enhance the out-of-plane toughness of the material system during impact and other loading events. So that's
Absolutely.
primarily why we focused on Kevlar. We did not look at other fibers such as Nicolon or anything like that, given this is a polymer matrix system. We didn't explore any high temperature materials such as things or pre-ceramic polymers or anything like that.
Yeah, well, Kevlar makes sense in that case. Good. I'd like to come back around and back to Dominik. Dominik, what would you say was the most surprising, interesting discovery you made within your research?
The most surprising thing, well, that was kind of the final results I got, that we saw that crystallization can already happen during forming. So what we always assume is that we stick to a certain processing window if you're forming thermoplastic tapes. But what we saw is if you make an unreasonable or unfavorable choice of your processing parameters, it induces already a crystallization or recrystallization already during forming, which then in turn distinctively influences how the formability looks like in the end. And I was quite surprised by that fact, because thermoplastics can cool down so fast during processing, and I was quite happy that we could model or predict this based on the model I have developed during my studies.
Oh, very good. Thank you. Pierre-Yves, one more question for Pierre-Yves. Do the gaps become acceptable weak regions during fiber placement?
So the advantage of the approach proposed, the holistic approach, is instead of going in and guessing or having to test the whole structure, eventually you're able to map those gaps onto the actual structure and test the final part or simulate the final part into FEA. And this kind of approach can then eventually be automated to assess the size of gaps that would be acceptable. So initially, instinctively, you'd say that ideally you don't want gaps, but when it comes down to laying down tape on a part and building the part with automated tape placement, because of the limited length in tape and the different curves and shapes that we're going to build or are being manufactured, eventually there's going to be for sure gaps within the structure. So the idea is with this approach, we're trying to put more emphasis on the simulation before jumping into the real production of a part and making sure that we're producing something that is relevant.
Great, thank you for that answer.
Mm-hmm.
Hugh, I have another question for you. On page 13 of your paper, right Fitster, you mentioned that this is a four-point bending test with DIC, digital image correlation. But seems that I don't see the sample being painted and speckled, which is common with DIC. Is it on the back side of the sample in that particular example?
Yes, so let me share my presentation so you could see what I'm talking about. So this is the picture that you mentioned probably.
Mm.
And so yes, so in this picture, on this surface of the sample, we did not show the speckle pattern. It's actually on the other side. And so as you can see, there's like the DSC camera in the background here, and then there's a light behind the setup, and then there's another light here. So it doesn't show, it's not shown on that picture, but for example, in this image that I show later, you can see the speckle pattern on the failed sample. And then on the VIC result, you can kind of see behind the strain contour, I mean the strain field, you can see the speckle pattern that was applied to the sample. Yes.
Oh, certainly. Okay. Very good. Thank you. Scott, another one for you. What is the advantage, Scott, for the OCT samples to be overheight?
Yeah, so there's, I don't know necessarily advantages, but kind of requirements. And maybe I'll share my screen just to show a little bit about why. Can you see the presentation there now?
Yep.
Yeah, so this is the overheight compact tension coupon. It's actually an ultrasonic scan of the coupon. And then the damage areas are, you kind of got the initial notch here on the left, and then it's being loaded vertically in this case. And ideally you want stable propagation of damage. And to get stable propagation of damage, you basically need a bunch of elastic material around the fracture process zone to keep the sample intact and prevent it from just catastrophically failing. You also ideally want a certain amount of distance between the fracture process zone and then the boundaries of the sample. So kind of this separation distance. And the way that the damage is going to propagate is very dependent on the material system and then the orthotropic material properties of the system. So in case A, and these are just rotated 90 degrees from each other basically. In case A, you can see we got lots of splitting and delamination. So that's propagating in that direction where we've got the overheight aspect. So that's, you can kind of see why you would want that overheight size sample, so that if you do get splitting and delamination, it has somewhere to go and still keep some elastic material around the edges. The other main reason is what we've seen in the past, when you have pins that go through these holes here, and then it's loaded vertically. And because of the orthotropic nature, orthotropic strength of the material, you can actually basically shear off these wings before or while you're getting damage at the end of the notch here where you would like it. So obviously it doesn't help you if you shear off kind of the material that you're using to load it. So that's the other main reason.
Okay, very good. Thank you. Daniel, I have a question for you. What is the extent of fiber damage or distortion in typical stitched laminate? Is it an acceptable damage to have improved interlaminar and G1 C properties?
Yeah, so it's an important question that we've been doing ongoing work to continue to characterize and quantify in order to really understand how various levels of stitch density is going to impact performance. So in follow-up work that was completed after the paper was initially submitted, we continued doing ASTM standard tensile and compressive testing. Compression testing actually finished up last week, so we're in the process of doing all that data reduction. But tensile testing showed that if we go from a stitch density varying at 8 stitches per square centimeter up to about 30 stitches, so quite dense in terms of stitch locations, we only saw about a 10% knockdown in total strength. And we saw about a 7.5% reduction in modulus. So we feel that given you're seeing over 100% increase in toughness due to the increasing in stitch density locally in mode 1 toughness, we feel that a 10% trade-off in tensile strength and modulus is quite reasonable. We've done a lot of work using X-ray CT to characterize the distortion regions, and the distortion in the local vicinity of the fiber is quite small and leads to very subtle variations in the actual fiber orientations of the principal fiber direction. So we think that it's a pretty reasonable trade-off that you're seeing locally very small distortions and manipulations from the CT scale that we're looking at on a voxel size ranging from about 10 microns up to about 25 microns. We're not able to visually determine if any fibers have been broken due to the stitch process, but we are able to identify any fibers that have been pushed out of the way during the stitching process, and we can locate those quite readily and reliably.
And from your research, would you say that you don't observe broken fibers because they don't exist, or you just can't find them, or what would that be?
I think it would be pretty bold to say that there aren't any fibers being broken during the stitching process. I mean, inherently, it's a fairly violent way of forcing Kevlar material through the carbon fiber preform in order to generate that local reinforcing. So I'm sure that there are small amounts of fiber being broken, but we feel that it's a pretty small second order effect based on the work that we've done to date. Okay, great. So we take the 10% knockdown, and that correlates for tensile properties, et cetera. I mean, if you're able to take a 10% reduction in local strength and reduce your weight by 30%, I'm sure for quite a lot of applications, that's an acceptable trade-off. Sure, absolutely. Okay, great. Okay, I think what I'd like to do is go back to the front. I don't see any of the questions coming in from our audience at this time. So what I will do is I've got some more questions for each of you. Dominik, could you share, you shared a little bit about what was most surprising. How do you see the future influence of this project?
So the future influence of this project is mainly that we have spun off a company from KIT to bring to the industry what we have developed in research. So this is the main idea. So this means that we supply the code we have developed for, so this is what I have to mention maybe. What we have done is to implement add-ons for Abacus, so that you can use Abacus for advanced thermoforming simulation. So this is basically how it works. And what we have now is a spin-off company. It's called SIMUTENCE. It's a spin-off company from the KIT in Germany. And what we do is to bring the code as a software add-on to the industry. So this means that we supply this code. And what we do also is to supply engineering services. So this means that we address companies here which do not have the expertise in-house for doing these simulations, that they can come to us and we run the simulations for them. And to say, okay, if you have a certain design for a thermoform part, can we manufacture it or not? Or what process parameters do we need to set for being able to manufacture the part? So this is mainly where the research is going at the moment. Okay, so next steps? Yeah, next steps is to further develop maybe the code also for further classes of materials. So I think it's pretty settled for thermoforming itself, but there are other interesting topics. So a big process we see there is wet compression molding. So this means that we have a dry fabric, which is in a certain areas soaked with a matrix or with a resin, and then we have a combined forming and infiltration just in one step. And it's an open mold process. And this is where, yeah, basically research is going now. This is what the colleagues back at KIT are focusing on now. So this means that the code is also going to be able to model an instantaneous forming and infiltration. So the keyword here is a fluid structure interaction. So this is something which is not possible at the moment, and this is what they are going or are focusing at the moment. Oh, very good. Thank you.
Pierre-Yves, could you tell us a little more about what you see the future influence of your project?
I would say right now, one of the biggest trends that I've seen, or at least things that I heard a lot about manufacturing using thermoplastic, is a lot of the parts that are being built are tested. So the testing is not necessarily at the material level, but people will build the parts and then they always go back to testing the whole structure. And what I'm hoping to see, and the trend that I'm hoping to see by using such approaches and connecting and generating multi-scale type modeling, is an adoption or a broader adoption of simulation, both at the design and the manufacturing level. And yeah, broader implementation, because right now, like I said, we see a lot of testing, but not necessarily big implementation of digital twin, and maybe, yeah, opening the road to more complete digital twin and representation of the parts themselves in simulation.
And next steps?
I would say next step, I think there is still things that are not necessarily included in the current modeling approach. So a lot of the things that we're currently including in the multi-scale approach are more at the mechanical level, but then eventually maybe including more manufacturing type information, crystallinity, bonding between the different plies or tapes that are being deposited, and the whole introduction to the thermal profile, so we can actually have a more complete material characterization, or at least material information. And then that's going to be probably, that would be the next step.
Okay, very good. Yeah, exciting stuff. Hugh, the same kind of questions. What do you see in the future as far as influence of this project, and what are the next steps?
Yeah, so Dow is a material supplier, and so ultimately we want to formulate more and better material so that we can sell them. And so my work right now, we are trying to understand the behavior of these foams, and so ultimately we want to use the modeling approach to help us to help Dow make more and better material for the construction application.
Okay, so construction basically. Next steps on this, better products, I guess?
Yes.
Okay, thank you. All right, same question. Scott, what do you see the future influence, and what are the next steps for this project?
Yeah, so kind of the impetus for this project came out of, as I said before, the automotive industry. And I was able to attend a talk given by one of the Volvo design engineers a few years ago, and he gave kind of a non-proprietary overview of the level of detail that their crash simulations go into on the metallic structures. And it's really quite incredible to see how very little things affect the overall response of the vehicle in a crash. And so they've got, decades of work invested in making these very complex but still efficient numerical models to do their crash simulations. And nowadays they basically only actually crash physical cars just for the certification process. So there's very few, if any, prototype crashes. And now with fuel efficiency regulations, lightweighting of vehicles becomes very important. And actually, even for electric vehicles, lightweighting is quite important because the batteries are so heavy, but also limit range. So any mass you can cut out of the car elsewhere in the structure is quite important. So automotive is, looking towards more use of composite materials. We've seen it in the BMW i3, i8, and then the 7 Series. But their ability to do computational analysis is, not at it's good, but it's not at the level of where they're at with metallic structures. So the whole focus of this is really on helping them to have efficient but capable tools for modeling damage in composites, so that they can have a good way of doing their crash tests without physical parts. And then I guess next steps, in the work that we did, we saw maybe not quite as much delamination as in the simulation compared to the physical test. And we believe that's probably mostly due to the fact that right now the intralaminar damage model is disconnected from the interlaminar damage model, and it's well known that matrix cracks lead to delaminations when it gets to those layers. So working on being able to tie those two together, I think is an important next step. And we've done it previously using cohesive elements. We have some user subroutines for doing that with CODAM2 in LSDyna. But in this work, we made use of the tie break contacts, which are a much easier way of modeling cohesive damage in LSDyna without all the kind of effort of setting up cohesive elements.
And I imagine that some of the selective high strength steel interfaces make that computation quite difficult. Is that, you got anything to say about that?
As far as the joining composites with metals, or?
Yeah, or just reinforcing composites over the high strength steel in select areas, and what performance characteristics you can glean out of that stiffness, basically.
Yeah, I mean, so I know, I think it's the BMW 7 series on the B pillars. Yeah. They use carbon fiber as one of the layers. So there's obviously the high strength steels in there. So yeah, absolutely. I mean, that's obviously it's kind of proprietary as to how they developed that, but I imagine it was, if it was purely metal, they probably would have done it mostly with computer analysis. But given where we are in terms of modeling composites for damage, I imagine they hedged their bet and did quite a bit of physical testing with real life parts as well. So,
okay, I got one more question here. Scott, you said that you're focused on automotive industry. What other industries would you like to see this play out, work for?
I mean, impact damage in aerospace is obviously a big concern.
Yeah.
They've got much more history in dealing with it, and sort of sorting out what type of damage is too much versus what needs to be repaired, and they've got lots of repair processes in place. A lot of that's been done through physical testing again, though. So every time you build a plane, they use the building block design approach where you do coupon tests and component tests, subassembly tests, and work your way up. And so
sure.
it works very well. It's a very well structured way of proving that these complex structures are going to work, but it's time consuming and costly, obviously. And if we get more comfortable with being able to predict damage in composites through numerical analysis to the point that, as with the cars, the metallic cars, and they don't do an actual crash test until certification. I don't think that's currently something that people would do with composites. I could be wrong, but that's kind of the future, I guess. Yeah,
in aerospace, you're not as concerned with, well, you want crash worthiness, obviously, but certainly, the impacts that you get on the ground with service equipment in aircraft tend to be one of the concerns that we have with big composite structures, where you may have a large area, wide area impact damage that's not visible from somebody pushing against the aft fuselage of a 87 or something. So that's a whole different realm of damage, but it'd be interesting to see how adaptive this is in the future. Okay, thank you. Daniel, can you go back and reiterate on the future influence of this project and next steps?
Yeah, so this project has been primarily driven by the Department of Energy under the IACME figurehead, which is principally geared towards automotive industry. This project, however, is in conjunction with several aerospace companies, collaborating with both Airbus and Lockheed Martin in order to really flesh out this design technology and try to utilize it, as Scott had already mentioned, as a method and mechanism for replacing some of the timely and costly aspects of a building block approach. The idea being, if we can show that we can mimic coupon level behavior and then scale that up to element level or sub-element level component behavior and accurately predict damage response and damage growth and performance, that allows all of those OEMs a mechanism that's put in place for them to both test out design criteria and design plans, as well as reduce the time and cost associated with certifying components. So obviously that is a huge potential impact if we can bring down the cost associated with all those certification processes. The other added benefit of the approach that we're taking is not only are we looking at full TFP composite structures where you're having local variations in fiber direction, we're also looking at utilizing TFP as inserts into your standard prepreg unidirectional or woven components, whereby you're just providing local reinforcements. So the current work that we've got ongoing is looking at embedding these TFP inserts into bearing locations for unidirectional prepreg, as well as looking at how we can use this TFP and localized stitch reinforcement on angled brackets, as well as in TFP bearing coupons, to show how well our model can do in capturing that response, with the idea being we scale this up and continue to look at larger structures in order to see how efficient this computational method is.
Oh, very good. And the next steps?
So currently we are in the process of finalizing our initial predictions for the bearing preforms for both the TFP insert in the prepreg, as well as the initial bearing preforms for a standard TFP preform. We're also working on our angled bracket simulations. Those coupons have been fabricated, are actually at the machine shop as we speak. So those should be tested shortly and hopefully have good agreement with our computational models. If not, then we can go back to the drawing board and iterate on things that we can modify in the model in order to approach the failure mechanism better and try to capture that behavior as accurately as possible. The benefit of the software suite that we're using is it's been pretty well vetted, I'd say, over the years in use with unidirectional composites, as well as some textile work. So the different damage mechanisms integrate well together and play off of each other very well. There's a nice coupling between the cohesive surfaces we're utilizing for interlaminar damage as well as intralaminar damage via our XFEM cracks. So I think the methodology is certainly there. We've gone through this really robust process of characterizing the material system we're testing, and we're now in the process of validating our material response and predictions in order to show good agreement with experimental data.
Well, thank you very much. With that, I have no further questions for anybody on the panel, unless there's some last minute questions from the audience that you've got a moment here to put in. If not, well, I would like to thank you all for participating in this session. If after the fact you have any additional questions, feel free to fill out the form on the track landing page at SAMPE North America website, and SAMPE will follow up. Make sure to check out the content being released next week for the additive manufacturing track within this virtual series. So with that, I'd like to conclude the Q&A session, and thank you again to all of the panelists for all of their participation today.